Hello, hello. There we go. Yep, I'm Tom. I'm talking about minimum equivalence in random Boolean networks, elementary cell automata, and beyond, and also between, but the title was already long enough. So why do I care, and why should you care, perhaps? Well, the minimum equivalence concept has had great impact on elementary cell automata, and that's almost self-evident once you are familiar with it, but it does not seem to be very prominent outside of it. It's been, when I went through and read a lot of these papers, I barely found any mention of it at all. So I think there exists untapped potential for its use. So let's go a little bit in the background and make sure that we're all on the same page. Luckily, a lot of people have talked about cellular automata already. So I'll just refresh your memory. It's this idealized complex system. It's parallel, it's deterministic, it's uniformly connected, it's synchronous. And there's this special case called elementary cellular automata, where you have specifically three neighbors, one dimension, one spatial dimension at least, two states, black or white, or many other names. And this system forms 256 distinct rules. The example here being rule 110, because its output of the transition table is the binary number there that translates into 110 in decimal. If you're familiar with cellular automata, random Boolean networks are not that hard to think about because they're very much like them. They're synchronous, deterministic, but there's two main differences. One is that they're randomly connected, and as well, there's also a random rule in each node or each cell. Let's see, I'm just going to watch my own slides here. There we go. Now, there is this little distinction that might be important between homogeneous RBN and RBN. Homogeneous being the type where you constrain so that every single node has the same integrity, meaning the same number of neighbors. And in this case, in this diagram, I've also, if I can find my mouse, there we go. If you're familiar with transition tables, there are many ways to display them. This is one. And under here is a different one that is relevant later when I go through some of the transformations. But those are essentially equivalents, but they're just different ways to project the information, really. Okay, so what about intermediate substrates? Well, turns out that there are a lot of names here. People use a lot of different names, which makes things confusing. But as I said, there's two main differences between RBNs and cellular automata. So naturally, there'll be two natural intermediate substrates. One where you just mix the rules, where every cell is a different rule, sometimes called non-uniform CA or hybrid CA. I'm not talking about that a lot today, but the other one I'll talk a bit more about, or is more relevant, which I call homogeneous RBN. So it's homogeneous because it has the same integrity, same number of neighbors, but it's also homogeneous because they all have the same rule. And this is also sometimes called non-local cellular automata, graph cellular automata, automata networks, or cellular automata networks in some regard or shape. Yeah, and if you were particularly attentive, you would actually have noticed that you can't actually tell if this is a homogeneous RBN or a RBN. It's in fact a homogeneous RBN because if you can compute this in your head, the example execution is actually, they all have the same transition table. Okay, so let's actually explain the minimum equivalence as well, as it is in elementary cellular automata. So many of you are at least familiar with rule 110. It's this cool rule that's Turing complete, but you can transform the transition table in such ways where you can create equivalent setups. So for example, if you do reflection, you can switch right and left. And if you do that for the initial condition as well, you can quite clearly see, I think, that they are doing the exact same computation. In fact, you can use one to replace the other, which means that rule 137 is also Turing complete. Because they have the exact same computation. You can also do the same with doing the color switch or the live dead black or white switch and do the complement where you take 0 and 1 and swap them. And if you do the same for initial condition, again, you can get the same computation. And of course, you can combine both of them. Now, this is actually a very old concept. It was first in a PhD by Creighton C. Walker that I could find in 1965. Working with not elementary cellular automata, but with something that's very similar, where it has random right and left neighbor, but always self-central. And it works exactly the same there. So it's actually a very old concept, which is kind of funny because the first publication that we all know about in cellular automata is from 1966, though it was talked about in the 40s. Okay, so let's get to the core. Let's talk about RBNs. This is a little toy example of an RBN. You might notice, if you're very attentive, that these do not actually tell you what the order of the neighbors are. That's not in the diagram. That's quite common for these examples. So there are, because there are 3 neighbors, 6 different combinations these can be in. And this gets very relevant very soon. Because you can take this information and you can swap between them, right? So because you're in RBN, it's arbitrary which gets selected, which means you can also swap the neighbor order. And you can that way turn, for example, 170, as you see in the example there, where you swap the second and third with each other. You turn that into a new transition table and reorder it so that it comes in the right order that you always have. And it turns into rule 204, which is not equivalent in Cellular Automata, but in RBNs, it turns out it is. So if you do that for the entire rule space, there we go. It turns out that there's only 80 rules that are unique under this transformation already, which is already less than you find in elementary Cellular Automata, where there's 88 if you apply both complement and reflection. So what if you apply complement as well, which is pretty much the same transformation? Then you turn into just 46 rules. So it's even smaller again, though there are some distinctions about when you can actually use these transformations in the different substrates. It makes a lot of sense to use it in homogeneous RBN, not as much in RBN to do the complement, though the switching is fine, though we can get into details about that. I don't have really time to explain all of it. But also, very interesting thing that happens in RBNs and these intermediate substrates is that because you have this switching set, the larger the in-degree, the larger amount of equivalence you can find. So if you have an in-degree of 4, you have 65,000 different combinations of that. But actually, under just the switching transformation, only 6.1% of that is actually unique, because you can transform between the other ones. And if you can apply complement as well, only 3% is unique. And this will probably continue to grow if you go up, but of course, the set becomes very large very quickly. So why is this useful? Well, a lot of people do exhaustive search in these substrates as well. So by reducing that, you save time, something we all like, I think. But it's also very interesting for understanding the substrate. What is the level of unique computation in your system can be very relevant when you're trying to analyze it. But also, I want to stress that it can also be used in optimization, because by having a lower amount of rules in your system, you can optimize the memory footprint. So you can fit it into a larger cache or a smaller cache or a smaller memory footprint, which can actually increase your performance as well. So this is a quick fire round, I guess, where I'm just going to talk about many different concepts. What about totalistic RBNs and Cellular Automata? Well, the switching and reflection doesn't make any sense here anymore, because if you're totalistic, that means you're just essentially counting your neighbors. But the complement's still relevant there, but no one ever seems to use it. What about non-binary substrates? Can we think a little bit about that? Yes. Although this explodes very quickly in how large these rule sets are, even in small ones, it's still possible to think about this. And in how it transforms very much the same way switching does, where you can switch between different color schemes, and they'll be equivalent informationally. But also, if you work with totalistic systems, it's actually viable to do it for much longer. So what about 2D Cellular Automata? Here also reflection changes. It's now also, if I have my hand, this is the same shape, but so is this, so is this, so is this, right? Makes a lot of sense. So you end up with sets of 8 for the switching or the reflection that are equivalent, or 16 if you can add complement as well. And this is, of course, very hard to exhaustively search the entire space of the Morse neighborhood, but it's starting to feel a bit more possible with the von Neumann, because that's just 4 billion, or 2 to the power of 32. And if you can reduce that space, it starts to become a little bit viable, actually. So why is this, what is the future of this? Well, in my opinion, this equivalence and the increasing power of our parallel computers gives options to exhaustively search spaces that we haven't before. So if you're interested, if you like and are very curious about different behaviors of spaces, this opens up some possibilities. And going through this also makes me think a lot about like what are the useful computation in your system. So perhaps you can do comparisons between totalistic and non-totalistic systems and see what the actual use of having a non-totalistic computational substrate is versus not having it. Okay, are there any questions?